Okay, I see participants slowly joining. Welcome, everyone. Today is one of the first webinars of Biocomem. Before we start, I want to let you know that as participant, you cannot speak nor switch on the camera, but you can write in the chat. So if you have any question for the presenters, please write in the chat and I will read for the presenters. I want to introduce now the coordinator of Biocomem, Dr. David from Technalia, who will give a very short introduction to the project. Please, the floor is yours.
Thank you very much. Hello, good morning, everybody. I will share my screen. Okay, confirm me if you can see well the presentation.
Yes.
Okay. So today we will show a few results that we achieve in Biocomem project, but to give an overall perspective, I will give a small presentation now. So Biocomem comes from bio-based copolymers for membrane end products for gas separation. It's a project where we want to demonstrate that membrane-based separations technique using PIBA-type polymers, so these are polyether block amide copolymers, are more efficient than their heat-based equivalent methods. Because we have an overall objective to reduce the impact of the industry at different levels. At the membrane material that we use level, the fact that membranes use lower energy than other separation options, and also the application we aim for is direct carbon dioxide capture. So we can have three impacts in the chemical industry to reduce the environmental footprint. So here it's a bit of a map of the partners we are involved in this project. We have two universities. This is Maastricht University and Eindhoven University. Two research centers, Herreon and us, Technalia. Two small companies, B4Plastic and Quantis, and one large company, which is Archem. And you can see some numbers about the contribution of BBIGU. And the project will end at the end of this year. Sorry for the date, it will end in November, so it had a 6-month extension. So the contest and the objectives are that we would like to decrease energy consumption, the overall sustainability and environmental impact of the chemical industry. And we believe that this PEBA-type chemistry can have this influence, because we will improve their functionality for higher processability into monolithic hollow fiber membrane, higher gas separation performance, and higher resistance to chemical attack. So this is a bit a map of the structure of the project. We have two main parts, which are given by the core work packages. So work package 3 and 4 are related to material productions and scale-up, and work package 5 to the validation of these materials. So we start from core materials. We start from bio-based monomers. Then we go we produce the polymers, which we are trying to transform into membrane structure with a commercial structure, an asymmetric structure, either by composite or monolithic hollow fiber. And then we check that we achieve the desired properties. And finally, we go to a demonstration in work package 5 at a TRL of 5 in a real gas facility, in this case for biogas upgrading. We have some activities which give support across the entire project. As usual, we have in work package 2, we have defined which are the industrial specifications, we are defining now the ideal process design with the real properties we got in the project, and we do technical and economical assessment. And in work package 7, we deal with dissemination and exploitation. And we also look at recyclability and plastic footprint in work package 6. So this is the entire structure of Biocomem project. And here I would like to show a brief overview of the results. We will go more into details later. So we managed so far to scale up, to screen more than 20 new BioPIBA copolymers, out of which we scaled up 4, which had the best properties. More than we actually desired at the beginning of the project, so we had very interesting results. And then we made biomembrane development at lab scale and at higher scale. So at higher scale, one of these 4 new scale-up BioPIBA are currently processed into monolithic hollow fiber membranes, which we call prototype B. And then 2 other more were scaled up as thin film composite membranes, prototype A and A1 to 10 square meter scale. And then we have another one, prototype C, which was scaled up to a smaller scale. So in the end, we have 4 scaled up membranes as well. And this is a bit the overview. Obviously, we have this main objective to bring a benefit to the society and the environment at the different levels, as I said before. So thank you very much, Fausto, and I give the floor back to you.
Thank you very much. As I see many participants just joining, as I said at the beginning, if you have any question, please write in the chat. And you see now the agenda. This was a very brief introduction of the project. I would like to ask Dr. Angels Ramirez to start with the first real presentation. And for the participants, every time, please write in the chat. I will read for the presenter. Please go.
Okay, thank you. Thank you, Fausto. I will share my screen now.
Perfect. You can go on.
Okay, you can see it, right? Everything's right.
Yes.
Okay, so thank you for the introduction. So my name is Ángeles Ramírez Cantún, and on behalf of the Institute of Membrane Research at the Helmholtz Zentrum Herion, I will present today about the development of thin film composite membranes. So to start, let's talk about who we are. So our Centrum belongs to the Helmholtz Association, which is one of the largest scientific organizations here in Germany, and which comprises 18 centers. Our centers, so Herion is located here north of the country, actually very close to Hamburg. Now, Herion comprises 15 institutes, which are dealing basically with material science and climate and coastal research. Now, our institute, so the Institute of Membrane Research, is part of the information or the material science branch, and is dedicated to the development of membranes for gas, vapor, and liquid separations. Now, our institute follows the entire research and development pathway in the membrane process development. That is from the polymer synthesis and modification to the polymer characterization and the preparation of integral asymmetric membranes, which will be in turn integrated into membrane modules that can be also incorporated into applications, whether lab or pilot plants. Now, this includes also the mathematical modeling such processes in order to facilitate the integration of the membrane module into a given separation process, and also to facilitate the quality control assessment. Now, our role within the Biocomem project, as Oana was mentioning, is to develop this flat sheet type of membranes, that is this thin film composite membranes, with these newly bio-based polyether block amide PBAs, which are designed by our synthesized by our partners, and as to use them as selective materials for separation. Now, with these membranes, we upscale them, and then we integrate them into membrane modules, which will be further tested by our partners in real applications. That is the separation for CO2 from several gases, and namely for the post-combustion flue gas treatment and natural and biogas upgrading. Now, how do we do this? Now, the general methodology for the development of a thin film composite membrane starts with the reception of the polymer. So the first thing we do is a general characterization of it to determine the glass transition or melting temperatures, and also the chemical and mechanical stabilities. Then, of course, we need to choose the most suitable solvent for the polymer in order to prepare dense films, and this will allow us to determine or to study the intrinsic gas separation properties of the polymer. Now, if we are satisfied with them, then we can proceed to prepare thin film composite membranes in the lab, and follow up with the morphological characterization, and along with the characterization of the gas separation performance of such membranes. So if we are satisfied with this performance, then we can continue to upscaling of the membranes, and of course to test the reproducibility of the membrane preparation, and also the quality control before we can place these upscaled membranes into membrane modules. Now, just as a reminder, we have different gas transport mechanisms that can be taking place in a membrane, and this will depend on the nature of the membrane. So in the case of porous membranes, we can have, depending on the pore size, of course, different transport mechanisms, which include viscous flow, Knudsen and surface diffusion, and molecular sieving. But what is of most interest for us is the solution diffusion transfer mechanism through of a gas through a dense or solid polymer membrane. And this is described by three main steps. That is the solution or the sorption of the gas molecule in the membrane interface, that is on the feed side. Then the diffusion of this gas molecule across these transient free volume elements within the membrane, and the final desorption of gas molecules on the permeate or the low pressure side of the membrane. Now, this transport mechanism was described by Graham by this following equation, describing the permeability as a product of the diffusivity and solubility coefficients of a gas in a polymer. Now, in this sense, the permeability can be defined as the amount of gas that can travel through a given thickness of polymer during a certain time and at a given membrane area when certain gradient of chemical potential is applied. So in the case of gas separations, this is the differences in pressure. Now, the diffusivity designates, kinetic factor, which indicates the probability of a gas molecule to move across these transient free volume elements within a polymer. And this will be given or mostly determined by the size of the gas molecule. Now, the solubility is a thermodynamic factor, and this will indicate the amount of gas that can be solved or dissolved within the polymer under equilibrium, and this will be determined by the affinity of the gas towards a certain polymer matrix. Now, this whole process, as you can see here, it's a thermally activated process. And from this, we can expect, for example, that the diffusivity will increase with increasing temperature and the solubility will decrease with increasing temperature. Another very important parameter is the selectivity for a given gas separation, which will be defined by the ratio of the permeabilities of the fast to the slow to the slowest gas permeating component. And now an example here about the units that we use for these separations. If we have a permeability coefficient for a given polymer and a given gas, so a gas X, for example, of 100 barrier, and we have selective layer thickness of around 100 nanometers, we would get a membrane permeance of around 2.7 cubic meters per square meter hour and bar, which will be equal to 1000 GPU or gas permeation units. Now we come to the choice of which polymer to use. And so for gas separations, we use normally amorphous polymers, which can be above or below their glass transition. Now, in the case of glassy polymers, we see that they are the diffusivity will be strongly depending, as I mentioned before, on the kinetic diameter of the gas molecule. We see here a strong dependence. So the smaller the gas molecule, the faster it will diffuse through the polymer. Now, this is not the case for rubbery polymers, as we know that in this state, there is no restriction for the movement of the polymer chains. So the gases pass easily, sort of saying, through the polymer. However, in the case of rubbery polymers, we will see that the solubility will play a major role, and this will determine, the final permeability of a polymer. So, for example, in the case of the separation of carbon dioxide and nitrogen in flue gas treatment, as these are the two main components, it will be advised to use, for example, rubbery polymers, as the solubility of nitrogen and CO2 are quite different. So this will be determined in the required separation. Now, before we start testing our polymer as we receive it, and as I mentioned before, we need to prepare a dense films. So to do this, we need to choose the right solvent for the polymer. That is the one that gives us a homogeneous solution. And then we need to filter the solution in order to eliminate any impurity that will affect the measurement. Then we pour this homogeneous solution into level Teflon molds, and we apply a constant nitrogen flow in order to have a regular solvent evaporation, and also to keep the polymer at the most equilibrated state for the film formation. So when the weight of the film is constant, and then we proceed to dry this film into a vacuum chamber to eliminate all solvent traces. And then we proceed to measure, for example, density, and most importantly, the thickness of the film. And now when we have this polymer film ready, we proceed to characterize it via the time lag method. And this method will consist in exposing the polymer film to a constant pressure of a given gas, and then observing how this gas diffuses through the known thickness of the film, as we can see here. And this is done by observing the permeate pressure in a calibrated permeate volume. This after previous evacuation of the apparatus. Now, from this plot, as we have an example here, we can determine, first of all, from this slope, when the measurement is at its steady state, we can determine the permeability coefficient. And from the time lag, that is the time that it takes the measurement to reach this steady state, that is the transient state, we can calculate the diffusivity coefficient. And now with these two parameters, we can already calculate the solubility of a gas in the polymer. So from one measurement, we can obtain the three most important parameters for the gas transport in a polymer. So now, if we are satisfied with it, we continue to prepare membranes. And for this, the most important feature that we need to consider is the thickness of the selective layer. Because as we see here in the definition of the permeance for a gas, the permeance is inversely proportional to the thickness of the membrane. That is, the thinner the selective layer, the faster the membrane will be. And this is what we need in order to use this membrane for a practical application. So if we are talking of membrane or selective layer thicknesses of that are in the nanometric scale, then we need, of course, the right support for it. And this is how we come to the concept of a thin film composite membrane. There is a membrane that is formed of different layers of different polymers, that each of them with a specific function. So we start with a very robust non-woven support that gives easiness of handling of this membrane. And on top of it, we prepare a porous ultrafiltration membrane, which will allow this selective layer membrane to be resistant when it's operated at higher pressures. Now, on top of the support, then we can coat different very ultra thin layers, which are the gutter, selective, and protective layers. Now, the surface, I mean, the porous support, it is one of the most important parts of a thin film composite membrane, as I mentioned before, because it allows these thin layers to be used at pressures up to 100 bar, for example. And the most important feature of this type of ultrafiltration membranes is the surface porosity. Here we have the example of a polyacrylonitrile porous membrane, which is a very robust polymer. And we can see here that the the pore sizes range from roughly from 5 to 40 with an average pore size of 20 nanometers. That is, these pore sizes have to be smaller than the thickness of the selective layer that we are planning to deposit on top. So here we have for this type of membrane of around 15%. And this is, as you can see, not too high, and especially considering that polyacrylonitrile is a non-gas permeating polymer. So in order to improve the gas separation performance of the membrane, we can proceed to coat or to activate the support by the deposition of the so-called gutter layer. And this very thin layer, which we coat by using, for example, polydimethylsiloxane, which is a very fast polymer with a very low selectivity, but fast and very robust, that is solvent resistant and has adhesive properties. So this layer, this gutter layer, will act as a very smooth and adhesive surface that will facilitate the addition of the selective layer on top. And most importantly, will work as a drainage layer of the gas, as you can see here, from the selective layer to the next available pore. So this will make the membrane faster. And now, when we have already the gutter layer, we can proceed to deposit our selective layer. And this we do it by means of a modified deep coating method at our institute, which is called the meniscus coating method. And this is done in a pilot scale machine comprising a 2-roller system, as you can see here. So we place the coating solution here in this reservoir, and then we roll the porous support on top of it. So if you can see here on the next image, we see in this small gap, my pointer is a little bit slow, sorry. So we see that this small gap here, that this meniscus is making the solution in very small contact surface with the porous support, and as the membrane is drawn out by the means of the roll, we have and the continuous evaporation of the solvent. We have to say here that the coating solution is very diluted. This allows us to get a very thin layer of polymer on top of the support that is under 100 nanometers. It is also important to say that we have also mathematical modelings describing all this process in detail for those who are interested. Now, as I mentioned, this coating procedure is modified meniscus coating. We do it here in this pilot scale membrane coating facility at our institute, which allows us to prepare membranes with lengths of up to 250 meters and widths of around 60 centimeters. And during membrane preparation, we ensure the quality control by taking samples at regular intervals across the membrane batch, and then measuring the oxygen and nitrogen selectivity, permanences and selectivities. And here in this particular example, we have the quality control for membrane envelopes of our polyactive membrane, the benchmark membrane of our institute. And we can see that both the permanences for nitrogen and the selectivities for oxygen nitrogen are quite consistent across the whole membrane batch. Now, a further characterization that can be performed in the developed and upscaled membranes is the one that is obtained in this so-called pressure increase facility, which is very similar to the time lag facility. And that is, it uses a constant volume variable pressure method. And with this method, we can characterize, or we can investigate the performance of a given thin film composite membrane for a wide number of gases. That is, we can measure here up to 15 different gases and at least one vapor in order to cover all possible applications for the given developed membrane. And this method will give us also very important data that will allow us to make modeling of the performance and to adapt the membrane into a desired membrane module for a given application. Now, when we are happy with the membrane, if everything is working correct, then we can proceed to integrate them into membrane modules. So here we have some examples of the most used membrane modules. For example, here we have a hollow fiber membrane module, but since we are dealing with flat sheet membranes, here we have an example of a spiral wound module. But here at our institute, we are mostly working with these envelope type modules. Now, these type of modules consist of several envelopes which are stacked into a perforated permeate tube, as we can see here. And each of these envelopes are separated by sealing elements in order to have a seal between the feed and the permeate sites. And this type of module is designed in such a way that the gas flows the longest time along the membrane surface. Now, this envelope stack is subdivided in compartments, as you can see here, divided in compartments by baffle plates. And each compartment will contain a certain amount of envelopes in order to treat the desired amount of gas for a given application. This is one of the advantages that this design offers. Now, we have different types of modules depending on the application. We have for piloting applications, this small module here that allows to have a membrane area of up to 1 square meter of membrane. And then we have these bigger modules, which can house up to 75 square meters of membrane. And they will be different depending on the, of course, the operating pressure that they can withstand. So for the standard module can operate to pressures of up to 20 bar, and this high pressure module can operate up to 100 bar. Now, here we have some preliminary results that we obtained within the Biocomem project. So as Anna was mentioning, we got one of the prototype PIVAs that we worked with. We were able to prepare a thin film composite membrane here on this PDMS and PIN support. We upscaled the membrane. We prepared membrane envelopes, and we fabricated some membrane modules and for a lab and for piloting applications, which will be tested by our partners. And now we can see here that, I mean, this in this little table showing the transport properties of carbon dioxide through this polymer at 30 degrees, we see that from an initial permeability coefficient of 165 barres, which gives us the potential application of the polymer to be used as a membrane, gives us a permeance, a final permeance of around 2000 GPU when this polymer is used as a ultra thin layer in a composite membrane of around 80 nanometers thickness. And if we compare this new developed membrane to our benchmark polyactive membrane, we see that for this block copolymer, this, for example, it is a lot much faster than the polyactive, but it has a lower selectivity. And actually, this is not so bad because we could use this membrane for a first stage separation in the treatment of flue gas, for example, which is actually quite nice, as this type of membrane will implicate to use a less membrane area for such application. And finally, and as a summary, we can say that thin film composite membranes, they can be produced from both glassy and rubbery polymers, and they, as I mentioned, they offer us the possibility to use the same supports for various selective layers and to apply these previously developed technologies into membrane packing and into membrane module fabrication. Now, this multi-layer membrane design also offers us the flexibility in the choice of a given material. And also a very important thing is that the fabrication of such membranes requires a very small amount of selective material per square meter. So around 100 milligrams of polymer for 23 square meters of membrane, for example. So this opens the way for experimental polymers and to be used and tested for real applications. And finally, the Institute of Membrane Research here at Helmholtz Zentrum Herion has extensive experience in membrane technology. So from, as I mentioned, from polymer synthesis up to a pilot scale application for a given separation process. And that's it. Thank you very much for your attention.
Thank you very much, Angels. There was a question from Raquel Jimenez, or do you already answer in your presentation? Perhaps you can go where you show the CO2 methane selectivity and CO2 permeance, because that was the question. Yeah, that was the question. Can you say how far we are from what the target was?
From the selectivity, we are a little bit far away. I mean, it depends on how you look at it. I think we were aiming to get selectivities in the range of the ones of polyactive. Actually, if we take a look at the selectivity of the polymer as a thick film, we we get very high selectivities for example, for carbon dioxide and nitrogen, or even CO2, methane. But of course, when we come to the real application and we come to a very ultra thin layer of polymer, then we of course lose this selectivity. And this is always, it comes always to this trade-off between permeability and selectivity. What does one want? Do you want a fast membrane, but you also want a selective membrane? So there's, I mean, unfortunately, we cannot get both until now, right? So this is what we are trying to get. I mean, with this polymer, I mean, yes, we get a very fast membrane, which is quite nice, but of course at the cost of not such a high selectivity. But I would say that 3031, which is the one we have here for CO2 nitrogen, it's actually not so bad and can be interesting for further application, especially for flue gas treatment.
Thank you very much. There was also a participant that had the hands raised. Please write the question in the chat, because in this way we will give the question to the presenter. By the way, there was a thank you from Raquel Jimenez. I don't see question coming. Anyway, we will have time at the end for additional question in case. Then thank you very much. And I would like to give the floor again to Dr. David.
So thank you
for the presentation. You can stop sharing, and thank you very much. Then Oana, please go on with your presentation.
Well, good morning again. Thank you, Angeles, for your presentation. It was very nice. So I just took off some slides from mine because you already explained very well a few concepts. Okay, so I hope you can see my screen.
Yes.
So today I would like to show a bit how I will speak about monolithic hollow fiber membranes and what is our strategy for their scale up. I will give one example from a different project, and I will also show a bit the results from Biocomem, just a few results. So again, why are membranes so important? So in this graphical representation at the left side, you can see at least in the US, half of the energy is used in separation processes in industry. Sorry, a third of the energy use is used by the industry, out of which half of it is used in separation processes. And here is where membranes have a lot of room if they become better a bit, because there are many separation processes like distillation, drying, and evaporation that are heat-driven. They involve a phase change. So because membranes do not need a phase change, the energy use of membranes is much lower. In addition, they have other advantages, like they occupy less space, so they have a smaller footprint. And actually, this is very important for carbon dioxide separation, for instance, because there is huge quantity of flue gas released, and you don't want to have a big separation processes. Like in the case of cement production, some calculations show that with conventional carbon dioxide capture, you would need a plant for capture equal as size as the plant for cement production. So membranes can have a lot of impact there. In addition, they are very simple. You can, if they break, you can just change a few models, and they can operate under continuous and steady state conditions. So if we speak about gas separation only, there are a few applications. These are carbon dioxide capture, methane purification, hydrogen purification, olefin paraffin separation, and water separation. And if we speak about classifying the membranes, these classifications can be done according to the material, to the structure, or to the geometry. So according to the materials, we can have inorganic membranes that can be metallic, ceramic, carbon, or zeolite, or organic, and these are polymeric. To the structure, we have something that are symmetric. These are thin films. They are not actually commercial membranes. And the really structure that is important for commercial perspective is the asymmetric structure. And this can be composite, as Angeles showed before, or integral asymmetric, which is what I will show now. And according to the geometry, they can be flat sheet, tubular, or hollow fiber. A hollow fiber is like a tube with an outer diameter lower than 0.5 millimeters. So going more deep into different commercial applications that are today, like state of the art, we can speak about hydrogen recovery in different separations, like syngas or hydrogen from nitrogen. And here we use polymers which are glassy, polysulfone and polyimides mostly. Nitrogen production or air separation basically with membranes is mostly done with polyphenylene oxide. Natural gas treatment is done with cellulose acetate or polyimides, and vapor recovery is done with rubbery polymers. And then, as Angeles was mentioning, there is a normal trade-off between selectivity and permeability. So a polymeric material that has a very high selectivity for a given separation usually has a lower permeability, and the opposite. So there is a limit, a trade-off. There is a limit that many people are trying to undertake to improve membrane properties and undertake this limit. And now coming to hollow fiber membrane. So here, as I said before, a hollow fiber, it's a tube with a lower diameter than 0.5 millimeters. So they have a few advantages mostly in terms of packing density, because in this calculation, you can see here in the graph below left, we calculated the surface area divided to the volume that these fibers would occupy inside a tube, which is equivalent of a separation module. So when the size becomes lower than 0.5 of the outer diameter of the fiber, then there is an exponential increase in the membrane area you can pack inside the tube. And this is one of the advantages of this geometry. And this is called packing density. So the square meter of membrane area divided to the volume of the module where you place the membranes inside. Normally, they can also work up to 70 bars. This is also important. And now going to the cross section, they are monolithic normally. We have a top layer, mostly on the outer skin, that is dense, and this layer ideally should be lower than 1 micrometer. Even 100 nanometer would be the limit, but would be very nice to have that without defects. And then below that layer, we have a porous part. And it's important to understand that both parts are made from the same material at the same time. So this is integrally skinned. And because of this process that is occurring at the same time, the formation of these two parts are occurring at the same time, normally the fabrication costs are much lower if we compare to composite membranes. So here a bit the spinning process, how it is. In this example, we show the co-extrusion of 2 polymeric solution, but it can be also of 1 polymeric solution. As here in the image before, this was made from 1 polymeric solution. We have a spinneret that is a needle in a needle. We form the hole by flushing through the inner side a bore liquid, which is usually a mixture of a solvent and water. And then the porous structure is formed in the coagulation bath, where there is a phase change. There is the solvent is very important for the solvent of the polymer to mix well with the liquid that's in the coagulation bath, normally water. And in between, in the air gap, which is here, there is evaporation of the solvent towards the exterior of this nascent fiber, and here this one promotes the formation of the dense skin outside. And after a few baths and washing, we collect the fibers in wet state. And then we have to dry them to have them for gas separation. So the structure is formed at the same time, and the following step before making the modules is drying of the fibers. And in comparison, a deep coating, for instance, in this case for a hollow fiber, is done like in several steps. Here you already have to start with the porous support and do the coagulation and do the coating. So we assume that is a bit more expensive. The only disadvantage of monolithic hollow fiber membranes is that you cannot use any kind of polymers. Not all of them are able to be processed in this way. So this is the objective of Biocomem, to tune the chemistry of PBA types polymers to be able to spin them in a hollow fiber membranes. So as Angelis was mentioning, here also we normally start, like when we develop hollow fiber membranes, there is a lot of work because there are many parameters to vary to actually obtain this ideal structure I was showing before. So we have to be sure that it's worth it. So we start with defining target performance for a given separation, and then based on that, we select a material, a polymer, or we develop, as in the case of Biocomem project. Then we make dense films, and we determine the intrinsic separation properties, which is the intrinsic permeability and selectivity. With this, we validate that the selection of the material was done properly, and if not, we just select another one. Then we start actually working. Like in this spinning process, we do many experiments to develop the monolithic hollow fiber membranes. In order to know if we achieve the optimized structure, we have to characterize them. So we determine the permeance and selectivity. We do this in a few iterations, and if we cannot, we have to. If we don't manage to achieve anything, we will have to go back to material selection or development. But if we are happy with the results, we have to start with a scale-up and prototype production. I will give an example. I would like to go more into details about this spinning of monolithic hollow fiber membranes. I will give an example from M4CO2 project, and in this case, we were developing hollow fiber membranes made of a polyimide, which is P84. In here, the right side, well, at the left side, you can see the structure, the chemical structure of this polymer. And at the right side, you can see like a comparison between two different polyimides, P84 and matrimide. So matrimide is a bit more permeable, but a bit less selective. So we manage here. So normally when you make monolithic hollow fiber membranes, you can have some defects on the outer skin. So from time to time you have a pinhole in this dense layer, and here also a PDMS layer as a protective layer can actually seal these defects. So instead of having air, you have another material here, which is PDMS, and this has the advantage that you can actually use the selectivity of the rest. So the pinhole is not decreasing anymore a lot the selectivity of the material. But we actually managed to have this P84 polyimide monolithic hollow fiber membranes without any defects, and now I will show you how. So again, going back to the spinning device, there, as I said before, there are many process parameters we can change. The most important is the dope composition. Afterwards, when we actually do the process, we can change the dope flow rate, the bore composition, bore flow rate, the spinning temperature, coagulation bath temperature, air gap height, take-up rate, room temperature, room humidity, even the coagulation bath liquid. We could vary in principle. We are trying to stick to water because there are huge volumes involved. So, as I said, dope composition is the key parameter. And this is like a three-phase, a ternary diagram. So we usually have three components in this dope solution, at least three components. So the most important is the polymer itself and the solvent. And then we can have some non-solvent. We start with the dope composition here given by the point in the blue point. We have already some non-solvent inside because we want to be already close to this boundary, the binodal line. So here is where this separates this mixture in two regions. The one in the left is one phase, so everything is miscible, and the polymer is liquid. And this two phase is when you actually form the coagulation of the polymer and then the pores inside this layer. So we want to be close to this phase change, close to the coagulation of the polymer. This is where we start with the dope, with the blue line. And then we have to define where is this boundary line, basically, for a new polymer. And also another analysis which we do is we need like sufficient viscosity for the thread to be self-sustained, like not to break during spinning, the wet part of the fiber when it comes out of the spinneret. So for that, there is like a minimum concentration we need to have, and we can determine this concentration by making several solutions with different polymer concentrations inside the solvent. So these are more simple solutions. Okay, so going back to our example, here we had as solvent NMP, we had a non-solvent ethanol, and we also added some THF in NMP. This is like a co-solvent up to a concentration. If we have only THF, then it behaves as a non-solvent. But the main point of THF is that it's more volatile than NMP, so it can promote the outer skin formation in the air gap when you have evaporation of the solvent. So the first study was like to determine how much THF we can add to NMP. And here we saw that there is a separation, a coagulation, if we have this maximum, the minimum ratio NMP to THF of 0.52. And then the next study was to see how much ethanol we can add as well in this dope composition, the non-solvent, to be closer to the boundary. So this is what we did. And afterwards, we used like different dopes to see, to make the spinning experiments. So here we have different NMP to THF ratio in these dopes. And we had the best results with the one that had more THF inside. So when the NMP to THF ratio was equal to 1. And this was dope 5. And what are better results is when we had a selectivity closer to the intrinsic selectivity of this polymer in terms of carbon dioxide to nitrogen. And now if we go to the details of DOP 5, here speaking about the other process parameters, we also played a bit with the spinner temperature and with the air gap height. So here I show in this graph the extremes. So it makes sense now that if you increase the air gap height, you increase the selective layer thickness. So at a very low air gap, we got like about 100 nanometers, and at a higher air gap, we had about 400 nanometers. So at a higher spin temperature, also the selective layer thickness was higher. Because of a higher selective layer thickness, the carbon dioxide permeance is lower. But what was surprising was that in this case, also the selectivity was lower. So in other words, we achieve at a higher air gap and a higher temperature, higher thickness of the selective layer, but also more defects. And this is without any PDMS coating. So this is because there is some humidity absorption from the environment, because we were not using any dry, like nitrogen flow in the air gap. But it's good that at very low air gaps, we did achieve very good selectivities. And then we also have higher carbon dioxide permeance. So a few images of the fibers of the two examples at these two very different air gaps, 2 and 10 centimeters. And also by same representation, it's observed that the selective layer at 2 centimeters is thinner than at 10 centimeters. So the first image is the entire cross section, then the fiber wall, then the selective layer, and the last image is the outer surface. And here also on the outer surface, the surface is more neat. So there are less defects at the lower air gap. And we also scaled up this fiber production, and we achieved very good results without performing any PDMS coating. So now I will go to example 2, to bio-based hollow fiber membranes, so the ones we are doing in Biocomem project. And here, just to have an overlook, we have 3 research lines. The BioPIBA line is a polymer that was already developed by Arkema at the beginning of the project at TRL 7, and they even increased the production, so they have it for some other application. But it's very good for carbon dioxide separation, and it's half bio-based because only the polyamide block is bio-based. It's coming from polyamide 11, which is derived from castor oil. The polyether block is fossil-based, and then Herion show you the results of composite flat sheet membranes. And then in Tegnalia, we are working on prototype B. So here the chemistry of PIBA type polymers was tuned to be able to spin them as monolithic hollow fiber membranes. That was the main objective. So we actually kind of kept the polyether constant for the moment, and we focus on changing the polyamide chemistry to be able to make spinnable polymers. And then we also had another research line where we had the main objective to develop a complete biopolymer. And here we played with both blocks to have them bio-based. So like what I show here, polyamide 11 for the polyamide was the starting point, but then in the project we change also the polyamide part, and the polyether part are all bio-based in the final prototype C. So a bit, speaking about PIBA type polymers, as I said, they are block copolymers. They have like a few repeating units of each polymer, not many, like 5. And because of that, you can achieve a very unique structure. You can have actually the rubbery polyether oxide, very amorphous, and it's stabilized mechanically by a few units, like faces, these fibers of polyamide blocks, which are more rigid. So this composite structure is mechanically very stable, and it allows for the polyether oxide phase to be in rubber state, which for carbon dioxide separation from nitrogen is highly important. So if we go to a few examples of copolymers that have been developed in Biocomem project, here from 1 to 6, in the second column, you can see the melting temperature of each block, polyether oxide and polyamide. Both are important. So for instance, for copolymer 5, if we have a melting temperature of polyether oxide of 16, then a normal operating conditions of a membrane technology, the whole polyether oxide would be like in a rubbery state, because we would speak about 30 degrees. And the polyamide here in this case is 80. This is the melting temperature, so it's a bit at the lower limit. After this, we also improved a bit the melting temperature of polyamide, and now we have about 120. But these are the first batch of polymers that have been screened. And here we got a permeability of 237 bar and the selectivity of 30.1. And here I'm speaking about the polymers that have been developed to make hollow fiber membranes. So this I give like an image of the spinning of this polymer. And these are like the hollow fibers that have been achieved in by spinning, and the image are for wet hollow fiber membranes. So we are still optimizing the process to get this ideal structure, and because we are writing a patent, I cannot show much more results right now. So thank you very much for your time, and if you have any questions, please let me know.
Thank you very much, Joanna. And indeed, if you have any question, please write on the chat. There is a question that is probably for the previous speaker, but perhaps you can also answer. And was, what is how the cost compares between the flat membranes and the hollow fiber membranes? And this from Alfredo Pacheco.
Thank you, Alfredo. It's a very good question, and we are trying to answer this question now. We have quantities. I don't know if we are doing techno-economical analysis in the project, so I cannot answer right now this question.
Okay, so in the next webinar, probably
yes,
we will say
I will write it
what
down. Yeah.
Good. I don't see any other question. In any case, if there are a question, I will ask you later, Joanna. Thank you very much.
Thank you very much.
And in your time, I would like to give the floor to Dr. Ramazzani for the presentation. Perfect.
Yes.
You can go.
Thank you, Pastor. Good morning, everybody. Thank you all for being here. I'm Ruzbe Ramazani, a postdoc researcher at TUE, Eindhoven University of Technology, and today I'm going to talk briefly about the membrane process design, cost analysis, and the simulation optimization. So far, you noted related to Biocomem project, we are trying to develop to fabricate a membrane for gas separation application. So in this project, our main focus is three main applications, which are post-combustion CO2 capture, biogas upgrading, and natural gas separation. So in theory, not only we are scaling up the lab scale setup to investigate the performance of membrane in the experimental point of view, but also from the economic perspective, I'm working to find out how this membrane is good in real industrial application. So from the economic point of view and the power consumption, so we're gonna talk about that. So let me start with a short introduction. As you already know, burning fossil fuel as a main energy source emit a massive amount of carbon dioxide in the atmosphere. So carbon capture and storage is one of the important technology to address this challenge. So of course, we have different methods to absorb CO2 or at least minimize emission of carbon dioxide. So which are, one of them is membrane gas separation technology. But the efficiency of this process strongly depends to performance of your membrane. So as you already listened to the previous two presentation, we are working to improve performance of a membrane in selective membrane selectivity or permeability point of view. But you know, there is a trade-off between them, so we cannot improve or increase both at the same time. So when we increase one of them, another one decreases. So, and this one, because the efficiency and the cost of your process depends to your membrane properties. So what we can do is or improve the membrane property to reduce the cost, or another alternative solution could be right process design or optimize your membrane-based process design to achieve your target, which can be your high gas recovery or purity at a minimum separation cost. So let's start. The first step is for you have your membrane. You're gonna see how your membrane behavior in the industrial application. So you need to know for which application you are going to use your membrane for post-combustion, for biogas upgrading, for natural gas. So you have different condition specification for your raw gas, right? So then you need to define your product, your separation target, your product quality. So which recovery or purity you want. And also then you can make decision which fellow configuration you want, co-current, counter-current. We're gonna discuss it later. And then based off the design and optimization, you can find out how many membrane stages you need. So then in details, you need to define economic model, you need to do optimization to reduce the separation cost as much as you can. So the simple configuration flow sheet for a membrane gas separation is one membrane stage, right? So basically we have our gas, depends to which application it is, or let's say post-combustion, it's gas coming from at 1 bar, so you need the compressor to provide driving force for your membrane. So then you need a heat exchanger to reduce the temperature, send it to the membrane. You have separation, retention side, permeate side. The permeate could either pass the vacuum pump or another compressor to go to the next step, right? But there is a problem here, or there's a challenge here in case you want very high purity or very high recovery. In single stage, you cannot achieve that, or you need very, very good membrane, at very high selectivity, which is, for example, in post-combustion CO2 capture, which now polymeric membrane, they are about 50 selectivities, 50, 45, 60. So you need the membrane with 200 selectivity to achieve that 90-95% recovery purity at one single step. So what we can do is to add another membrane cell. Let's see in the two-stage membrane what happens. So, but depends to what you want. It's your gas mixture is CO2 nitrogen or is CO2 methane. You can have, for example, for CO2, you need your product is in the permeate side, but for CO2 methane, your product is in the retention side. So 2SH to achieve the pure retention side is this configuration, but for example post-combustion, this configuration could be your option to have the purer, more high purity for CO2. But the question here is this flow sheet and optimal configuration. This is only one, or we can have other fellowship. You can recycle, you can add more splitter, more mixer, and play with these two membranes. So what we have done at TUE is, before that, I mean, you can add more membrane stage, 3 or 4, but you cannot just add recycle stream or add connection this line to that line. So you need to do correctly. So what we have done is we did superstructure at TUE. So we gonna let the software to decide which configuration is best, is the best one in a cost point of view, of course, for our specific application, right? So I think, can you hear me now?
Yes.
Okay, sorry, I just disconnected for 1 second. Sorry. Yeah. I was saying, so we started designing superstructure membrane design. So here you can see we have 3 membrane stage, right? So we have our feeding gas. So of course, it passing from our first feed compressor, increase the pressure. Then we have a splitter to adjust our feed gas. So it could send to the first stage, second or third one, depends to optimization. Then we have a few mixer, splitter, and 3 vacuum pump for each stage. And then, of course, heat exchanger, compressor, and at the end, the final compressor C4. But this is a superstructure we used for 3 applications. But there are some minor difference between 2 applications. For example, for post-combustion, our product is in the permeate side. So we need also to increase pressure to liquefy carbon dioxide. So we need another compressor as a C4 to increase pressure from 1 to 76 bar. And then we add another pump to increase to 150 bar, right? But we don't need that one, a compressor C4 in natural gas or biogas and biogas upgrading. And also here, expander for post-combustion, we don't need. The pressure retention side is descended throughout. But for natural gas or biogas, depends to your pressure in the grid. So you need that you can have compressor or expander, okay? So it depends to your final pressure. But this is a simple I just put here. So we start with we know our application, we know our feed gas condition feeding. So we use this superstructure. Then to achieve our gas pure objective target, which is a very high purity and recovery, depends to our gas mixing, CO2 nitrogen or CO2 methane. So let's move on. So first, we make a decision about which fellow configuration you need for your membrane design. So it could be co-current, cross flow, or counter current. We started with co-current. Then you need to choose which software you need to do simulation of your process. So we decided to work with Aspen Plus as a powerful simulator, but you don't have the membrane module in the Aspen Plus, so you can use Aspen Custom Modeler to add the membrane block in your process in the Aspen Plus. Then you can start your completing your design and the simulation. Then after that, you need to define your economic model because you want to achieve your separation target at the lowest cost. So your objective you need minimum GPC or gas processing cost in your objective, your optimization objective. So we did cost analysis for 3 different applications. we calculate capital cost and operational cost for our three applications to see what is our separation cost and compare to the conventional technology. So here there is our economic model, the cost for each item, for compressor, for electricity, for membrane module, for everything. You need to calculate it. You need to find out the equation. Then you can calculate your gas processing cost. But here, this equation is for post-combustion. It's a bit different for natural gas. You need to also calculate amount of the gas for methane. So now we designed our superstructure, right? We added many splitter with the purple color. You can see it is about 7. So it gives us good flexibility. Many possible configuration you can have with this with this superstructure. Okay, so you can have even without recycling. You can have recycle from only one stage, but we need to make to do optimization to find out what is the best configuration based on our application. So we need a few decision variables. So for optimization, which are membrane area or for each stage. Another one is the retention pressure or operating pressure. We here assume the pressure for retention is the constant and is the same for all stage. Another one is the permeate pressure for each stage can be different with another one, which is the between 0.2 and 1 bar. And of course, the split fraction, right? So, but the good point here is after optimization, if one splitter send flow to your membrane stage and the flow rate is 0, so you can consider that, ignore that stage. So you can say, okay, 2 stage is the best option for our case. So as I was saying, that was our decision variable. So you need your input variable. They are constant, feed condition, membrane selectivity, membrane properties, of course. And you need to know your target pressure. Of course, you have your objective. You want to achieve that purity and recovery at the minimum gas processing cost, right? Then the output of your optimization would be the compressor power, your total membrane area, CapEx and OpEx, and of course, separation cost. So let's start with the first result of the optimization. We did all this. We tested this superstructure for 3 different applications to see to check feasibility of the superstructure. If it worked for all 3 different applications, because they are completely different with different gas feeding and different product targets. So let's start with biogas upgrading, which in the biogas, we want to increase purity of the methane from 60 to about 95. It could be more, but here we assume 95 purity and 90% recovery. And of course, biogas has other more impurity, but here we just assume, okay, only a binary mixture of gas, CO2 and methane. And we decided to choose our product target is 16 bar. Okay, so we use that superstructure for this project target to see how to look like. So you can see in this structure for biogas, 2 option is the best one. 2 membrane stage is enough. We can reach to that target at the cost of the, if I can see, 69 euro per ton product. So we can 2 stage for biogas is the perfect. We don't need vacuum pump for first stage. We just need vacuum pump for the second one. We can reach to 95% methane at the second stage, at operating pressure of the 13 bar. So for this case, we need around 121 square meter membrane area. So let's check for another application. We also checked for natural gas. So almost the same, but a different gas composition, which is from 90% methane to increase to purity to about 97.5% purity at 98% recovery. So it depends to your gas grid. You need your specification. This can be changed. For example, here we decided to be at 20 bar, but it could be at even 40 bar. So yeah, here you can see the big difference with the previous application is for natural gas separation, we need 3 stages to have separation target at the minimum cost, right? So we don't need any vacuum pump for each stage. The 1 bar for permeate stream is fine. We have to recycle. So at operating pressure 21 bar, we need, of course, expander to reduce to 20 bar. So that the cost of the 17 euro per ton natural gas. So, and for the last application, which is post-combustion CO2 capture, we did more investigation. Of course, we have our feed condition, our target. Here is now our target here differences we have in the permeate side. So we want to have high purity CO2 from 95% to 98% at reach to 76 bar. We also investigate this superstructure, multi-stage membrane, from different point of view. I mean, from the minimize the capture cost, minimizing the energy consumption, and of course, as well as the membrane area. And of course, we did a sensitive analysis to investigate, to assess the effect of the different gas purity recovery on the cost and different membrane selectivity on the gas separation cost. Here, okay, this is the 3-stage optimal configuration, of course, for post-combustion to reach 90% CO2 recovery and 95% purity CO2. So, but the objective is to minimize the cost, so not membrane area or energy consumption. So here you can see we can have to reach to this separation target with 3 membrane stage at 59, about 59 euro, sorry, separation cost. And the specific energy consumption is about 30.3 gigajoule per ton carbon dioxide, right? And here you can see we need about 6,000 square meter membrane area. But here, in this structure, we decided to see how it look like if the instead of having gas separation cost in the optimization target, we're gonna have to see how to reach that target at the minimum membrane area. So here is the optimal configuration. You see here membrane area is much less compared to previous one, was 6,000. Now is 2,000, but of course the cost is higher, 70 euro compared to 59. So if the membrane area is your objective, you can reach to your separation target at higher cost, but at lower membrane area. And of course, I did also for energy consumption. So here, we also wanted to check feasibility of the superstructure at very high gas purity and recovery. Okay, so we did first start with 90 and 95% recovery purity. We also check superstructure at different gas recovery and purity. So even at 95% recovery and 98% CO2 purity, we can use this superstructure with 3 stages. We can reach the separation cost, but of course the cost is a bit higher, 90 compared to 59 at lower recovery. But usually in the post-combustion, we don't need that much high 95% recovery. So based on the literature, for if you are okay with 90% recovery, so this application could be competitive to the literature. And the last one is we also investigate the effect of the selectivity. Okay, if all the property is the same, permeance is the same, because now for post-combustion, the membrane selectivity is 25. Okay, so let's see if what happened if we can improve membrane selectivity a bit to about 50. So you can see the cost, separation cost, reduced about 28% from 59 euro to about 42 euro. So at the end, in this project, we proved our superstructure can work for 3 different applications. So we already tested for post-combustion, for natural gas, and for biogas upgrading. And also I did test for other application, hydrogen separation. So, and it can also work at very high recovery and purity. And the last, my comment is, we are going also work and to test other prototype of membrane at different selectivity and permeability to see how it's gonna be that cost analysis. And also I'm gonna to add more impurity to the gas mixture, not only CO2 nitrogen, maybe a bit some water, about 5%, 4%, to see how it's gonna be the effect of other impurity. Thank you so much.
Thank you very much. Okay, there were a couple of questions. One you already answered was about the split fraction of methane, but you already answered. And there is a question saying that some of the membrane technology claim 0.5% or 0.1% methane losses. So it would be nice to see what if this is economically feasible. I think you don't have an answer now, but it's a good suggestion for your simulation. Was from Raquel Jimenez.
Thank you.
Perhaps if you can make this calculation, then we can also answer to this question.
Sure. Okay.
There is another question. Just so the question is if these simulations are modeled in Aspen with custom model membrane. Is that the case?
No, we use Aspen custom modeler to add membrane block to the Aspen Plus. Then we integrated that one to the Aspen Plus. But then you can also do your mass balance or the component balance in your Aspen custom modeler. But it can also work for different component, different gas mixture, CO2 nitrogen, CO2 methane. Also, you can add. It's not can be only a binary mixture. It can also work for 3 or 4 components. But yes, we use Aspen custom modeler to have that membrane in our Aspen. Yeah.
And then there is another question. There are already membrane processes for natural gas treatment and biogas upgrading. I guess in the market or in literature. Have you compared against those processes to literature, for example?
Yeah, in the literature for natural gas, they most going with the 2-stage membrane, most of them, and they usually have their configuration, the just 2-stage, or just a few was 3-stage. They design it to have this configuration, not with optimization. But about the cost, for biogas, we are close to them. Is because our selectivity is about 8 compared to 14, 15. But we're not that much far about the cost. But for post-combustion, we are about 59 euro, which is compared to literature about 45 or 50 euro.
And for biogas?
Yes, biogas, our unit here I reported is based off the euro per ton, but usually in the literature is per of the cubic meter. But if we are converted, we are close to that natural gas and biogas.
Okay, So already with the membranes that we have, if you do an optimization, you get closer to
because to reach that one, or you need to improve your selectivity, or with 3-stage, because all we have in the literature is usually 2-stage without vacuum pump. But here we prove that with 3-stage and vacuum pump, you can even have less processing cost.
Great. Thank you very much also for the different questions. If there is any other question, please put in the chat and I will ask later. And now I would like to ask Dr. Freeland to continue with. Yes, I see you.
Thank you. Let me quickly share my screen.
I see the screen, you can continue.
Okay, perfect. So welcome from my side as well. I'm Stefan. I'm working for Quantis. We are one of the partners, so Anna mentioned, in the Biocomem project. And after now we've seen all the details in terms of the research that has been done on the membranes. I would like to contribute by spanning a little bit the bigger picture again, looking into how we can measure the bio-based solutions and in which methodology or which context this can lead to a proper management along the pathways of first assessing, then create the right action and being accountable for those actions. So I will give a quick introduction and context around the LCA, but also the project specifics here. Then we dive a little bit into the framework of LCA, why it is important, how it can be used, and then how to approach it right, because that's again two different parts of the coin. One is the intended use, and the other one is how to approach to make sure the intended use can be fulfilled. Then, after having this, let's say, methodological concept, we will look into how does it look now for bio-based solutions, and especially also compared to fossil alternatives or fossil conventionals, and how LCA can help to navigate within this space, but what is also maybe needed to go beyond. And closing with a few key takeaways. So quickly to me, I'm Stefan. As I mentioned, I'm working for Quantis. I'm a senior sustainability consultant. I have a background in plastics, more like on the freight and transport side of things, but still my connection to the project comes from the bio-based and biodegradable potential solutions towards closing or switching from more of a linear model to a more circular model. In general, Quantis, a few words about us. We are an environmental sustainability consultancy, and we work with brands across the globe to, drive the sustainable transformation of the different businesses, and especially to align with planetary boundaries, because of the fact we already have crossed several of those boundaries. One to mention specifically, again, in the context here, we have definitely the climate change, the biosphere integrity, and the novel entities to take a little bit into account. And at Quantis, we are focusing on 5 environmental expertise areas: climate, water, the plastic pollution or end-of-life aspects, as well land and ag, and biodiversity. We are a team of 250 people. We are spread mostly across Europe, but also we have a base in the US. And we are since 15 years in the business of sustainability consulting, where we are basically trying to work across 3 pillars, which is one of the assess side. So using the science-based method that are available to assess any given system, but then also to help based on the insights to plan and transform those systems. So a quick context now into the content itself. As we explore a little bit in this webinar the sustainable future of gas separation and the potential use of bio-based membranes for this one, we will also here look a little bit more into the integrated process of measuring the environmental impacts, and especially also thinking about trade-offs in the context of bio-based materials. Concerns over climate change and security, as well of industrial feedstock supplies, have been opening a quite growing market here for bio-based materials. And from the environmental perspective, it is crucial to assess the sustainability of new technologies that develop, for example, membrane system both bio-based as well as fossil-based play a significant role in gas separation processes. However, evaluating their environmental performance really requires a comprehensive approach, considering a range of factors. So especially when we think about trade-offs, we will look a little bit into this in more detail. So first of all, we will explore the methodologies and frameworks that are designed to capture and to help identify those potential trade-offs from an environmental perspective. And here we will discuss the life cycle assessment as a tool to evaluate those membrane environmental impacts, but also touching a little bit wider the concept of circularity and how it can help us quantify, but also minimize and capture trade-offs, taking a little bit of another angle than a pure LCA perspective. So first of all, LCA, 3 main points for this one. How can it be used in 3 different ways? First of all, is the assessment part of the thing. So that's a science-based tool or framework that help to measure product footprints and environmental hotspots across different sets of categories. And that depends a little bit on the sector, on the project, and on the specifics. But on the other hand, it can also use those metrics and insights in the end to guide environmental action. So let it be in national plans, but let it also be in more on the corporate level. This really can help on focus on priorities when it comes to the environmental sustainability, especially keeping in mind from the assessment the trade-offs that can occur. On another point, also LCA can then be used to correctly communicate with all type of stakeholders. So not only consumers, but also regulatory stakeholders, so to say, to help to adhere to new and more stringent regulatory frameworks that are really popping out currently, also especially on the bio-based context on a daily basis, you can say. So what is it? Why is it important, and how can it be used in the end? We want to understand from a perspective of eco-design how a product system can be improved in terms of environmental performance, taking into account still, the service and the performance itself of the product that is already available, to not, scrutinize this one by the new solution. So eco-design can be defined as the integration of environmental perspective into products and service design and development. Again, LCA, a brief overview to say, okay, why is it relevant to have a methodology framework, and why is LCA maybe the most advanced in this case? Because it is really a compass that can help guiding the transformation process. So in terms of the assessment, really understanding value chain hotspots compared to already existing alternatives to see improvements and relatively gains, but also potential limits. Then also avoiding to shift the burden by taking a multi-indicator approach. But then, as I mentioned, it goes further to, identify improvement possibilities, manage risks, and really get ready to make sure the newly developed solution also finds its application. But it doesn't mean if the use is defined, the approach to it is correctly done, because there are a lot of things to consider when doing a life cycle assessment, especially in a complex field like bio-based solutions. Just a quick overview on the approach. It is really a matrix-based approach, so it allows an impact evaluation and comparison, and based on a credible scientific basis. It also helps to look at the product system, so taking a system perspective, meaning really a full life cycle perspective, and being able to highlight therefore also potential burden shifting from one to the other one, or unintended consequences caused by a new production in terms, for example, of end of life. As well, it is a multi-criteria approach, so if we can see we can cover a multiple range of indicators, again, with the perspective of trade-offs. And I keep repeating this because it's really relevant, especially in the case of bio-based solutions. So it is a good decision-making tool. Why? Because, again, hotspot identification, improvement identification, but also in terms of goals and progress measurements and benchmark performance, it can help a lot. Generally, the framework that's defined by ISO norms, and you see you have basically 3 or 4 main parts, which is the goal and scope definition, which is really crucial. The lifecycle inventory analysis, where it's basically looking at all of those different flows between technical and environmental systems, and then combining this in an impact method in order to understand the, let's say, ecosystem level implications. And why focusing on those different steps? And I quickly want to look at the goal and scope again in the context of Biobased. This is a very relevant distinction to make. You can see mainly the all relevant or important mistakes are made on the first day. In the case of LCA, that's really the goal and scope. There are a lot of lists. I don't go through everything that you need to take into account when you start to build a model, so to say, looking at a new system. But I want to highlight two specific ones where to deep dive a little bit more, because again, on the context of Biobased, you know, some are more relevant than the others. And here we, especially if you look about system boundaries, but also allocation procedures, you know, in terms of feedstocks production, that's a very relevant one. And in general, just to give the overview again on the system, and this is kind of replicated for Biocomem context, then we have resources going into a product system, and then we have a certain type of preparation to a certain type of feedstock. When then, you know, this goes through the infrastructure of the producer, the company, or whatsoever, including any transportation, manufacturing as well. And then at the final, you know, point of distribution, it goes into the use phase, which is also very relevant in our specific case in terms of environmental performance. And then it ends up an end of life potential with recycling, but also potential leakage due to landfilling as well as mismanaged waste. There are different scopes that we can look at. Currently, we've been focusing a little bit more on a cradle to gate. So that's really looking and understanding, okay, we have a specific feedstock, how all of those synthesis can be done to manufacture, let's say, the final module or the final product. And then we will expand this to the end of the project with completing the full life cycle of the project of the product system, looking into cradle to gate, including, you know, the waste implications, the use phase implications. And especially we had it already in the chat as one questions in use. We can think about what is the use of a membrane. I mean, it's not like a t-shirt that you buy and wash, and therefore you have energy impacts behind, but really in terms of use, we can more link this to the performance considerations, such as, for example, methane slip performance in the biogas application, etc., which has obviously, because it is accounting all emissions to air, water, and soil within this product system, a potential high influence on the final environmental footprint. Other boundaries, you can go even a little bit more when there's a specific focus on developing also, you know, for example, bio-based or biorecycling methods. Then this could also be expanded to cradle to cradle, or there's also a really a narrow focus which can be taken, which is the gate to gate, really looking at one value-added process in the entire chain. As I mentioned, once we have calculated and accounted for all of those flows, we have an inventory which is now integrated with, so to say, impact assessment methodology. You can see on the right side an example for the EF methodology, which is kind of giving 16 different indicators, potential indicators to look, you know, split it between ecosystem indicators, health indicators, climate change, resource, and water, helping to account for the trade-offs as mentioned. So keep in mind that LCA evaluate potential impacts, produce relative results. It provides a hotspot view, but it can or needs, not only can, but sometimes it really needs to be complemented by other additional insights. If we think about bio-based solutions, we want to understand also how much the solution is not only preventing more emissions, but also how much does these potential solutions help in order to keep, you know, or close a certain type of a loop in the economy and in the type of resource use, or at least using feedstocks that are renewable. It is not the risk assessment, and one thing very important, which is always, you know, the most delicate one, is uncertainty associated with data and therefore also results. So it is always in the needs of a practitioner, but also the context to really find a good balance here and being very transparent about any assumption or proxies taken if no primary data is available. To a certain extent, primary data is needed because else, you know, the range is too high. So to sum up on LCA itself, we are not speaking about the treasure map, but we have really a compass in our hands to understand where the new developments are going. and really help and guide, take decisions in maybe improving certain aspects. So now when we think about the context of bio-based solutions and having all of the LCI framework in mind, in the world of bioplastics, the term bio can have different meanings. So first of all, starting here, it can refer, first of all, to the use of renewable resources, for example, for monomers or polymers or any type of feedstock part or building block. Then it can also refer to biodegradability, production through biological processes, or a combination of all of these factors. So it's really important to also sort a little bit the different definitions and have a clear picture in mind. And it is definitely discouraged to use the term bioplastics for any fossil feedstock derived but degradable or biodegradable plastics. Again, spanning a little bit the picture, when we look at why we are talking about plastics and what is the current one that we want to achieve and why we have bio-based solutions in place, is we have a very linear model, as we all know, with high virgin feedstock production, which then goes into all of the different applications. But if you look at the gray part, the waste, we have a very poor or very small share of all of this global amounts only going into recycling, so potentially back to the loop, which doesn't necessarily mean that the 60% also be able to be used in the end, but we have a huge part going into landfills or unmanaged dumps, which is definitely raising the concerns why also bio-based solutions can play a role, which is the contribution to climate change. For example, in the EU, it is the third largest greenhouse gas polluter industry. Then we can also think about, as I mentioned, from the end-of-life perspective, the concern of plastic leakage, pollution, drawing back the picture to the planetary boundaries, where we cross the boundary for novel entities by a large margin, and leaked material, especially plastics and all associated additives and whatsoever, play an important role in this planetary boundary. So there needs to be a new paradigm, and there's a new paradigm also coming, driven by associations like Ellen MacArthur, for example. Maybe we need to rethink a little bit that plastics not in general, or the use of polymers, definitely not the problem, but it's how we use it and dispose it, and also how we build it. So potential actions are obviously after-use economy, but also plastic leakage reduction into environment. But one that we want to focus now is more on the decoupling the plastic production or polymer production from fossil feedstocks, and also considering bio-based plastic, again, thinking with potential definition derived from the feedstock, but also on the properties of end of life as a potential source to close the gap. And the circular model would look like this. We have a huge part of recycling. We have the feedstock question, design and production, use, and also then the end of life, which hopefully will not result in any potential leakage at the end. So here, obviously, recycling we leave out for now. That's one of the big chairs definitely to be done, but also bio-based renewable feedstocks can help as the input part already to reduce this overall impact of this, let's say, industry, and also helping to achieve this shift to more of a circular model. But also that biodegradable or compostable can help in terms of the end of life. Again, as I mentioned, bio-based is not biodegradable, so just seeing here a small overview. I'm not going to detail because I already shown, but there are different definitions, and it's really hard to navigate sometimes, especially for users in the sphere. We can also talk about compostable, which is another thing in terms of degradation, differentiating between industrial scale or home compostable, but that's really a different detail. And then we have also drop-in versus innovative polymers. So bio-based solutions, drop-ins are more like same polymer as conventional, but a little bit change of the feedstock, while innovative is really new polymers or polymers basically that haven't existed before. But we want to focus a little bit on the bio-based feedstocks, obviously, because we can use the inputs from the natural environment in a biorefinery produce similar or the same kind of feedstocks as we can derive from the fossil ones. So the question is now bio-based plastics, yes or no, and helping using LCA and some literature to shed some light on this, because it is very important to note that the sustainability of bio-based plastics is not guaranteed. So while renewable resource can really reduce carbon emissions, or also depending a little bit on how the renewable feedstock has been produced, also on land use, other factors through the life cycle can offset those benefits. Because for the crude oil production, we are not using fertilizers, we are not using land, and so on. At least that's not accounted for in the LCA framework, while definitely when we think about bioplastics derived from agri-based feedstocks, we need to consider feedstock harvesting, processing, and also the end-of-life scenarios. Well, that's for both fossil and bio-based. So the use of first-generation biomass remains really controversial, and for a good reason, because there's a potential competition with food production, as well as consumer confusion due to the inconsistent labeling and the need for improved information distribution and global standards to really contribute to also take the educational side of the thing with the journey. And looking a little bit into comparison now using LCA, you can see these are literature values in terms of just comparing. It's not the specific membrane, but comparing like bio-based polymers against fossil ones. And we see, the black bar always represents the carbon emissions. So we're just focusing on a climate change indicator here. While there's also a potential uptake that can be accounted for in the methodology, generating a net value. And we can see fossil PE in the middle, definitely in terms of carbon, has not always the highest impact. That's also lead very importantly when we think about the bio-based alternatives. Main drivers here have been identified to be process yields, but also the agrochemicals, as I mentioned, or deforestation. You can see, depending also on where it is coming from, these impacts play a huge role in terms of also then the carbon emissions associated. And then in the example of bio-LDPE from sugarcane, you can see the net value basically resulting in zero, taking into account the uptake. But if we would consider average sugarcane sourced in Brazil, this has a completely different in the end net value due to the fact of the feedstock being produced in a high area of deforestation. So this really makes it visible how important it is to consider, first of all, the feedstock and where the feedstock can come from. Then we have, this is still primary production. Now we look at a waste feedstock such as wood residue, and we can see we can even get a negative result due to the fact that a waste feedstock otherwise would have had some end of life emissions, which are avoided basically by using it as a feedstock for a new product. But as I mentioned, in terms of all of the different trade-offs, we can, well, in this case, we have in terms of water consumption, but also ecosystem quality or respectively land use. We have similar trends here, while it is like a little bit different. Still, we see in the ecosystem quality, the bio-LDPE from wood residue still has a certain type of a land use impact behind that, while we have seen before in the climate change, it was really going even in the nets zero, below zero, basically. So this shows us that, and this is a similar trend that if we look at membranes or any type of product produced in the end, and this is really credit to Gate, so only looking at the production, we have these type of trends to watch out in this project as well. And we've seen already first preliminary trends in this direction, but due to a narrow focus, we will wait until we have the full life cycle, including all the testing data included, so then we can have a full view across the life cycle. Now coming to the management part still, or wrapping basically quickly up, because I see we are a little bit shorter in time, but I just wanted to briefly mention, now we've seen all of these challenges. We might have an LCA result which gives like different a little bit of a different picture due to the potential trade-offs in between. Now, any company or anyone or any economy, so to say, who wants to implement now bio-based materials as a switch to fossil ones, has really to consider a certain framework, which makes it really complicated in terms of doing the right choices and having a full picture, because we have an average, we may have an average view from the LCA, but we have a lot of specific, for example, local end-of-life scenarios and so on, which are very relevant for regulations that are currently set up, or EPR schemes, and needs to be considered into again. But I don't want to spend too much time here, because it's really more like, an informative approach after having some insights from LCA and cost analysis and so on. This is still to be considered then in terms of application for any user of those new materials. So key takeaways, again, on LCA, well, it is a compass. It's really about helping to find the right direction and seeing potential burden shiftings from the start. It strives for progress over perfection. So there always is a certain uncertainty behind, but hotspots can still be relatively detected. Then it's also very important to go beyond the carbon tunnel vision. As we have seen, there are trade-offs potential coming from the switch to bio-based due to agricultural production to take into account. And for bio-based solutions, we can say that, first of all, bio-based does not necessarily mean more sustainable. It's not always the case, because thinking again on the first or second generation feedstock and how we can take this into account in a broader societal and sustainability system, in terms of food competition, for example. Then understand capture ecosystem trade-offs. As an example, 1 metric ton of bio-based polymer can save relatively like 55 to 34 gigajoules of primary energy relatively to conventional alternative, and also like 3 to 1 ton carbon dioxide. But it also may increase eutrophication by 5 or 7 kilograms phosphate, and also stratospheric ozone depletion by the nitrous oxide equivalents behind all of the feedstock production. Then, after we have these insights, still there needs to be defined an implementation framework in which all of these considerations are taken into account to allow really a transitioning and also adapted use of those new materials in existing solutions or industries, and to help to comply with all the regulations and certification rules. Well, a little bit over time, but thanks a lot for your attention.
Thank you very much for the nice presentation. I don't see still question in the chat, but I have a question myself. Can you perhaps indicate some source where we can read the results, because to me are very shocking. So going to bio-based seems worse than with oil. So can you perhaps indicate some source?
Yeah, definitely. So, I mean, it depends again a little bit in the specific context. So this was what I showed was, and I can happy to share the sources and the study. Where is it from? Like it's really looking at LDPE in a comparison, and it's really only looking at the cradle to gate. So this is just a first indication to show that we always have to watch out. We have seen in the preliminary assessment for bio-based solutions, depending on a few choices still to be discussed, that we have a potential gain across all of the indicators, while land use, we might have a little bit of an increase. So it's not always the same picture, but yes, I'm happy to share the study and so on afterwards. But this is really like, as I mentioned, it's just to make aware about the fact that bio-based, if we start then to compete against other feedstock production, we will always have, a certain limit to any benefit that can be gained from it.
Clear. Then no question anymore in the chat, I see. I would like to give back the words to Oana, the coordinator of the project, if she wants to say some final words before we close.
Well, thank you very much, everybody, for being here. I hope you had a wonderful morning and that you enjoyed our workshop. So please keep you updated on the results. We have a webpage as well, and we will post on LinkedIn future workshop. The project will end in November, and we will have another workshop by then, showing the final results. Thank you very much. I wish you a nice day.
Thank you very much to all. Thank you, Anna, and see you for the next webinar. Bye.
All right, thank you.